Operational amplifiers. So what are those amplifiers? Well, an amplifier is a device that accepts a varying input signal and produces an output signal with a larger amplitude. Okay, so what does that mean? Well, that means that if the input of the operational amplifier, you have a small signal, something like this, that is drawn from a mic, say, okay, and it goes through an amplifier. For amplifier, we also use opamp, that's a short form for it, okay, and our hope is the output signal that comes out of the opamp is actually the magnified version of this uh, input voltage right here. Now, there's one factor using which we characterize the performance of op-amp, which is referred to as gain. Okay, now what is gain? So say for this operational amplifier, the gain is 10, which means this input signal right here and this output side signal right here. This output signal is going to be amplified 10 times, meaning this signal is 10 times as big as this signal right here. Okay, so that's a basic, goal of an amplifier. But remember, there are various other applications of an operational amplifier, and I'll go through it at the end of this lecture also. But what we are going to do here, we are going to design the amplifier and study a little about the introduction to op amps from a very, very basic level. Okay, its design structure also. To start with, let's look at the block diagram form of some of the critical aspects of an op amp. Okay, so say you have a source right here, and I'm gonna label it as VS. Okay, and then, whenever you model a source, we always have this practical source concepts. You'll have this input resistance, and then I'm going to call this input resistance as RS, source resistance. We are going to drive this input signal to an operational amplifier over here. Okay, and our hopes would be this operational amplifier had some kind of gain, say A, and our hope would be that the output, which will be some kind of, say, resistive load. Again, this could be a speaker or whatever. Okay, that this signal that we get over here, the output voltage, which will be the voltage across this resistive load, is going to be an amplified version of the input signal, which is Vs. Okay, so this is what we are striving for, and it's important to keep this in mind. Vs, which is the input signal, A is the amplification factor, or the gain, and the resistive load right here, the voltage across that, which will be VL, is going to be the amplified version of the input signal. Okay, so this is important to keep this in mind because that's what we are striving for over here. Okay, also notice over here in this block diagram, we basically can characterize this block diagram into three kinds of components. The first component that we have over here is the input signal, right? That's the input signal, or, in other words, a source, correct? Okay, the next component is basically the amplification of the signal. So this is the amplifier right here. Uh, and then with this amplifier, we have the load that is connected, and therefore the third component is basically a load here. Okay. Now again, we go back to our definition of an amplifier. Okay, we want to boost the power of the input signal over here, and ideally we would like to see VL being the amplified version of the input signal. Okay, so now what is going to happen? Well, there are two things that may come to our mind, and it is important to answer those questions before we can move on. So what are those questions? The first question that may come to your mind is, what does source sees looking at the amplifier? What I'm trying to say here, so say you are source, okay? What does source sees looking into the amplifier? Remember, source connected to any device may consider that device as a load. Okay, so op-amp might be considered as a load to the input power supply. Okay, so what does source sees? Well, source sees some kind of load which has some equivalent resistance. Some equivalent resistance. Okay, there you go. Okay, now second question. What does load sees looking towards the amplifier? Now what it means, so if you want to look at it from a perspective of a load, okay, what does load sees looking at the amplifier? Well, load looking at the amplifier looks at some amplified version of the input signal, okay? Amplified version of the input signal, which is the VSA, the input signal. Okay, so basically it sees some kind of source, right? Some kind of source. So, well, what does load sees? Load sees an equivalent, or you can also say amplified source. Okay, now I'm going to model the block diagram which I have over here into considering these two factors right here. Okay, so what's going to happen here is again I have this input source Vs. Okay, remember this is your input signal. Okay, whenever we model a practical source, we had the source resistance. I called it labeled as Rs. The amplification factor, the amplification block that I had over here, I'm going to remove it with what we discovered over here. Okay, what does source sees? Source sees some equivalent resistance. Okay, source sees as the amplifier as some equivalent resistance. I'm going to label that resistance as Rn over here. Okay, all right. I'm also gonna label this node as VP. This is positive, this is negative, and this node as VN. And then this VN right here is going to be the potential difference between VP and VN. Okay. The second thing was load sees an equivalent source or amplified source. How do you model that? Well, when we model a dependent source, in this case, it's going to be amplified version of the input signal, which is going to be Vn in this case. Vn, again, remember, this is the input signal right here, correct? And then whenever we model a practical source, it goes through some resistance, just like you had over here. I'm going to label this resistance as R out, and then this is connected to your resistive load right here. Okay, and then remember the voltage across this resistive load will be labeled as VL. You have positive and negative, and again remember VL, we are hoping that it's the amplified version of the input signal, correct? Okay, now what is amplifier block that represents over here? What is this block right here? Well, what goes inside this block is basically this thing right here. If I couple this thing over here, this is what goes inside an amplifier. You have the input resistance right here, you have the amplified version of the input signal, and then you have the output resistance also, right? Maybe I should do it like this. Okay, cool. uh, Now we have two cases here. Now if you look at it again from a perspective of a load source and amplifier, the first case is, in the first case, you want your Vn to be essentially equal to the source voltage, which is Vs. Okay, in other words, we want our input voltage over here to be as close as possible to this Vs, which means the voltage drop across Rs needs to be extremely small, and it's going to be very small because the value of the Rs is going to be in few ohms. Okay, so how do we measure or calculate Vn? Well, looking at this circuit, a series circuit, say there's some current flowing over here. If we apply voltage divider, we are able to find out the voltage across the input terminals, these right here in red. Okay, so Vn equals to total source power supply, which is Vs, times Rin. Okay, whatever the voltage across this resistor is actually the Vn, correct? Divided by total resistance, which will be the sum of these two, correct? Rs plus Rn, okay? And I'm gonna label this as this is my equation A. Okay, cool. The second thing here is that we would like VL to be equals to A dot Vn. Okay, all right. Now here, if I again apply voltage divider, whatever the voltage over here across the RL is the VL, correct? And if I apply voltage divider, I get what? VL equals to A dot Vn. Again, remember this source is basically the amplified version of the input voltage. So A dot Vn, source times RL divided by total resistance, which is again going to be the sum of these two resistance. So I have R out plus RL. Okay, equation say B. Now I'm going to come back over here to this point right here. And I'm going to say, okay, all right, we are striving for getting Vn equals to Vs. Vn equals to Vs. So I want you to focus on this equation right here, equation A. What should be the value of input resistance? What should be the value of the input resistance such that Vn is equals to Vs? Okay, and the answer is if I have my input resistance to be extremely high, say, infinity. Obviously, ideally we want it to be infinity, but in practical, it's going to be some huge number in, say, giga ohms or tera ohms. Okay, so if I put infinity in this equation A over here, what do I get? Well, Vn equals to Vs times Rn infinity. Rs plus infinity, correct? Now here in the denominator you will have Vs infinity, and then Rs plus infinity is going to be infinity. Infinity and infinity cancel out, and you get Vs. So your Vn is equals to Vs, and that's what we were striving for over here, correct? Okay, awesome. So in an ideal amplifier, we want this resistance to be very high. If this resistance is very high, means this voltage and this voltage will be very same. Okay, let's move on to the second case again. We would like VL to be equals to A dot Vn. So the question is, what should be the value of R out? Okay, remember you are an engineering designer, and it's up to you whichever way you want to design this. You have this option to choose a value for these input resistance over here and this output resistance over here. And again, because as an engineering designer, we can manipulate their values, we can change the characteristic of an amplifier such that they will have some kind of unique IV characteristics. Okay, and again, so we are striving for getting Vn equals to Vs. So what should be the value of R out? Well, if we choose R out to be extremely small, so ideally say 0 ohms, and if I put the 0 ohm value in equation B over here, then what do I get? Let's see. Well, VL equals to A dot Vn, correct? Multiplied by RL, so I get RL here divided by R out plus RL, R out being 0, so get RL here, RL cancel out, and we get VL equals to A dot Vn, and that's what we were aiming for, right? We were aiming for VL equals to A dot Vn, and then also we were aiming for Vn dot Vs that we got from putting the input resistance equals to infinity. So two things that we learned: in an ideal amplifier, we want the input resistance to be extremely high, ideally infinity, and then output resistance to be very small, ideally 0 ohm. Okay, all right. Now I'm going to take you to some theory right here. So some basic theory right here related to the amplifier. They first arrived on the scene in 1952. They were constructed with vacuum tubes and used in analog computers back then. They have many applications: filters, comparators, integrators. Back in those days, it was expensive, $75. They would dissipate a lot of heat. Now they are down to less than $1. Okay, and this is a basically a very um, common and very popular uh, 741 general purpose operational amplifier which has 8 pins. Okay, and what goes inside, they come in like IC packaging, and what goes inside those packaging, transistor, diodes, resistors, capacitors, and through integrated circuit technology. Okay, so what I was gonna share with you is, okay, what are the characteristics of the ideal amplifier? Now we do understand we want to keep our input impedance to be extremely high. Practically it's going to be in tera ohms. Okay, cool. We also going to have zero output impedance. Okay, why? Because we want our load voltage to be equals to gain times input voltage, but ideally it's not practically it's not zero, it's some small number. Okay, it's usually like 100 to 200 ohms. The third thing here, which is the infinite gain, and as I go along I'll explain you, I've already explained you what gain is, and we would like our gain, which is a as large as possible, and as large as it is, the output voltage will be large also. A few more things, but we don't need to care about it in this lecture. I'll explain in the future lectures. Zero noise contribution and infinite frequency bandwidth. Your ideal amplifier is supposed to have these kind of characteristics. Okay, now again, practically it's not possible to have those things, so therefore these are the practical values right here associated. Now I want you to introduce the schematic of operational amplifier. How does an operational amplifier looks like on a specification sheet? Well, the symbol is right here. Okay, it will look something like this, rectangle, triangle sort of thing. You have this input terminals right here. These are the input terminals. Okay, VP is a V positive terminal, also referred to as a non-inverting input terminal. VN is the negative terminal, also referred to as an inverting input terminal. Okay, remember we learned that our the input resistance needs to be very high, right? Ideally infinity. Then we have this gain, this dependent source right here, which is basically gain times input voltage, the voltage over here at these nodes, that's a VN, correct? And then R out needs to be 0, uh, and then this is your output voltage right here. Notice it also has these power supply Vs positive, Vs negatives. Uh, gain usually, amplifiers usually have two power supplies. Okay, the reason this device is capable of amplifying a circuit is because where is that power coming from? That power is actually coming from these power supply. Also, remember one thing, your output voltage is dependent upon these power supply, their ratings. Okay, so if these are like 9 plus and then say -9 right here, your output voltage cannot be above 9 volts. Okay, it's going to be within this range, +9 and -9. So keep that in mind. Um, some notations right here. What is I plus and I negative? Those are basically the current that's going in into the input of the amplifier. Okay. Um, Vin, we already talked about that. That's the voltage across this resistor right here. You have Vs and V minus. Those are this power supply, the two power supply. Usually they range between +15 to -15. Again, in the case of +15, -15, the output voltage is going to be between this range. Okay, it cannot exceed that. Input resistance is going to be ideally infinity, usually in high. That's the gain of the amplifier. R out is the output resistance. V naught is the output voltage gain. NVP and VN, I already explained over here what those are. VP being a non-inverting terminal and the VN being the inverting terminal. I'll also explain what those non-inverting and inverting input terminal would mean. In today's lecture, we're going to focus on the uh, inverting amplifier. So you'll get to know what the inverting input terminal is and also the output inverting terminal. So let's now look at the example of an ideal amplifier and then explore it a little. So I'm going to go back to the supporting material here. Okay, this is an ideal amplifier that we have designed ourselves. Okay, and I'm gonna quickly go through it. What did we decide? Okay, we have this input signal here. It goes through some source resistance. The input our resistance is going to be high, infinity. We have this gain dependent source, which is amplified by the voltage across whatever we have across this terminal. We name it Vn. Then we have R out, which is going to be 0 ohms. And then we have this output. Remember here, the portion of the output signal is feeded back into the negative terminal, which is V, and this is V node, negative terminal of the op-amp. This resistor is referred to as RF, which is the feedback resistor. Okay, and this route right here is referred to as a negative feedback, and because this feedback is connected to the negative terminal, it's referred to as an inverting amplifier. If the feedback is connected to the positive terminal over here, like this over here, then it will be a non-inverting amplifier. Okay, so remember that. And again, remember your output voltage is going to be A dot Vn. Now, I am going to transform this ideal amplifier over here into uh, into a circuit model. Okay, and before I do that, I also want to explain you one thing. We usually have negative feedback because it's connected to the negative terminal here. This feedback right here is considered as a negative feedback, which is desirable. And I want to give you this analogy. Whenever we go and take a shower in winter, we always have the struggle to find a balance between hot and cold, right? you know a little here and there, that would not be a comfortable way for us to take a shower. So that's what negative feedback does. You would know exactly when to stop, or when to just keep on going, more hot if you need, or more cold you may need, right? If you imply positive feedback, that's not how our body works. If that would be the case, positive feedback, what it does, you would jump into a shower, you would crank the hot, valve all the way to the very left, and then you will basically end up in a third-degree burn, right? So that's not desirable. Our human bodies also don't work that way. We have a negative feedback system. When we sense something, that there's something hot, we immediately remove our hand, correct? Now, transforming this circuit over here into a circuit model. So how it would look like. Now let's start from the VS here. VS, I'm going to say this is my VS positive terminal, and this is my negative terminal VS. And it's connected to the ground. Then I have the source resistance here. So this is connected to the source. Then I have this node right here, which is Vn. So I'm just going to say this is my Vn. This resistance right here is going to be extremely high. Remember, it's going to be infinity, right? So how do we model as something which is of high resistance that go down as an open circuit, right? So this will be an open circuit. Again, this is the positive terminal Vp. So I'm going to call it Vp. This again input resistance right here, because it is so high that we actually treat it as an open circuit, so I don't need to have it over there. And then remember, the voltage across these two terminal will be Vn. Okay, so Vn is equals to Vp minus Vn, and this Vp is actually connected to the ground here, correct? So I'm just gonna connect it to the ground. Okay, sweet. Now I have from here, I have this feedback, right? We just connected the output voltage. So I'm gonna run this wire like this, and then connect it to the feedback resistor, connect it to the feedback resistor here, and then it is connected to the V out terminal. Okay, remember I have RF over here. Okay, now I have this dependent source over here. I'm going to draw that depending source. So it will look like a diamond looking structure, and it's connected to the ground over here. So I'm just going to connect it to the ground. Again, plus minus, this is A dot Vn. Okay, and whenever you model a source, we have this R out right here, just like we have over here. We want that output resistance to be extremely small. If something is of very small resistance, how do we model it? Well, it's just a simple wire. Okay, no resistance. So I just connected to this node right here. Remember, this node is V out. Okay, this is positive terminal, and say this is the negative terminal. of the V out right here. Okay, now I have transformed that circuit into the circuit model. Now what I'm going to do, I'm actually going to apply nodal voltage analysis, and then I'm gonna do some manipulation to get an equation for the output gain. Remember, we are striving for V naught equals to A dot Vs, correct? And then output voltage over input voltage Vs is that's what the gain is going to be, correct? Okay, all right. So we essentially have taken a very complex device based on how it was designed or how we have designed it, and now we can present it in terms of the condition that can produce unique IV characteristics. Okay, so let's go ahead and perform a nodal voltage analysis, and we're going to pick the input side and apply KCL. Okay, what was KCL? Current entering the node equals current leaving the node. So current entering the node, okay, we're going to apply nodal voltage analysis at node Vn. Current entering the node equals to current leaving the node, correct? Okay, what is the current entering the node? That is the voltage across, that is the current across, basically you can apply Ohm's law here, right? So I equals to V over R. V would be the potential difference between these two terminals, right? So that would be Vs minus Vn. Vs minus Vn divided by source resistance Rs. This is the current entering the node equals to current leaving the node. What is that current? Well, that's the potential difference between this node and this node divided by RF, correct? So we would have Vn minus V out divided by RF, and I'm going to do some cross multiplication and simplify this expression. I'm going to label it as this is my equation C. Okay, remember V out, VO equals to V out. They are same thing. Okay, so this V out is basically uh, this VO and this V out is same thing. I just wanted to keep it small. So this, we have this equation right here. Now let's move over the output side. Okay, I want to focus on the output side of this circuit. And because we don't really have a good way of finding out how much is current entering this node. We know how much current entering this node, but we don't know how much is current entering this node right here. So we can't really apply nodal voltage analysis, but what we could do here is basically, apply KVL here, right? And in that case, if you notice, what are the polarities? We already know that we have plus here. If you're gonna go clockwise like this, so going from negative here, positive, so basically climbing up, right? And then go this way, and then you have V out plus here, and then minus. So you're climbing down the hill. Okay, so what would be the equation if you apply KCL? Not KCL, this would be KVL here at the output. So I get A dot Vn, which is basically the this source right here. And then because we're going from positive to negative, from higher pressure to a lower pressure, that would mean minus V out equals to 0. Okay, and if I push V out to the right hand side, I get Vi in A dot Vn equals to V out. Okay, and V out over Vn will actually give me this equation A, right? So remember that. Okay, also there are a few things that are pretty known from this circuit model, such that VP is directly connected to the ground, right? So this would mean VP is equals to 0 volts, correct? Okay, so I'm gonna come down here. Remember, we knew that the input voltage is basically the potential difference between VP minus VN, okay? Because VP is 0, so this would mean, and then also, yeah, VP is 0 here, correct? Okay. Now, I want to focus on one thing that which I forgot about it. Okay, coming back to this equation right here. A, we understand that input resistance, ideally we want it to be infinity. Want our output resistance to be 0 ohms, right? As small as possible. But what about A? Well, we would want it to be as high as possible too. We want it to be infinity, correct? So if I put that number in this equation right here, Okay, so say V in equals to V out over A, correct? A being infinity, V out, we know infinity is basically 1 over 0, right? So this whole thing will be 0, correct? So Vn is going to be 0, okay? Now, because Vn is equals to Vp minus Vn, we know Vn is going to be 0, correct? Which would mean Vp is going to be equals to Vn, right? If I push this Vn to the left hand side, I get Vp equals to Vn. And because from the circuit we know Vp is equals to 0, that would mean Vp and Vn are both going to be 0 volts, correct? Okay. Now, remember this equation over here that we have, okay? Um, you know, you would think ideally VP and VN needs to be, same, but in practical, there's a very, very small difference between that. It's usually like a micro and picovolts. And that difference, tiny difference, is basically responsible for the huge voltage swing at the output. So let's now move on. What do we have now? So I am going to plug this piece of information that I have over here, that VPVN equals to 0 in equation 1. So putting VP and VN both equals to 0 in equation, I believe it was C, right? This was C, correct? Yeah, this was C. So in C, now let's look at this equation. Because Vn is 0, that means this whole term will be 0, right? And then I would have basically these two terms on each end of the equals to sign, right? So I get Vs Rf, okay, equals to negative V naught dot Rs, okay? And if I do some cross multiplication, I get V naught over Vs equals to negative Rf over Rs, and we know the output signal over input signal Vs is equivalent to the gain, and that's what we got here. That gain is equivalent to negative Rf feedback resistor over the source resistance. In other words, I can also write this equation, A dot Vs equals to V naught. And if you recall, that's what we were striving for at the beginning of this analysis here, okay? AVL equals to A dot Vs. Now, how do we choose a gain for an amplifier, such as, let's say you have this um, LM741? Well, in a circuit, you choose the values for these resistances and you choose a gain for your circuit. Okay, so say you are looking for a gain of 1000, okay, of 1000. So I would choose my RF to be 1K and RS to be 1 ohm. Okay, so RF being 1K, which will be 1000, RS being 1, and that gives me a gain of 1000, correct? This negative sign here basically tells you or indicates that there's going to be 180 degrees phase shift. So the ideal amplifier that we had over here, this I'm gonna, if I want to keep a gain of 1000, I'm going to choose this resistance value for the feedback resistor to be 1K, and this is going to be 1 ohm, and at the output swing over here is going to be 1000 times as big as this input signal over here. Okay, so that's a very basic of the operational amplifier from a very basic level. This is, remember, an inverting amplifier. Okay, this is the inverting amplifier. Next lecture, we're gonna do non-inverting amplifier. I hope you enjoyed this video, and I shall see you guys in another one. Please subscribe to the channel if you haven't already.